Hi, Bailey.
Hi. How are you doing today?
Good, how are you?
Good.
Okay, let's get it started. So yesterday we started to talk about angular impulse and momentum, and we have been talking about the how can we do cross product and how we apply the cross product into the angular momentum equation, or the by multiplying the distance vector r cross product by the linear momentum vector. So let's do a quick review. So when we talked about uh, the angular momentum, so the angular momentum is the moment of the linear momentum about point O. And if we want to get this into a scalar form, so if you want to get the moment of any vector about any point, you will have to find the perpendicular distance between this point and this vector, and this perpendicular distance is d, and then you multiply it by this vector. And we are talking about scalar form, so we will have HO, which is the angular momentum, will be equal to distance d multiplied by the mv. So you multiply these two distances by each other as a magnitude, and you will get the scalar quantity of the angular momentum. However, in most of our course, we will be using the vector form. And for the vector form, we will have to have the angular momentum as a vector. And the angular momentum as a vector is something like, as we talked last time, it's like a rotational vector like this. And to determine the direction of the rotational vector, we will have to use the right hand rule. So you will have your right hand and curl your fingers towards the direction of the arrow and see what is your thumb is directed to. So for this one, you will have your thumb will be going this way. So it's a positive direction. If it's in the other direction like this, and you will be curling your finger like this, you will find your thumb is towards this direction. So this is negative and this is positive. And make sure to know this concept before the quiz, because there's a question in the quiz that has 2 points. Will be asking you what is the positive direction and what is the negative direction. So for anything, angular momentum, moment, angular velocity, angular acceleration, all of them is a curled curve like this in this direction. So all what you have to do, you will have your fingers and curl your fingers towards the arrow and see what is your finger is. If it's outside, like coming towards you, so it's positive, it's going inside the page, so it will be negative. And we discussed this in detail yesterday, and the angular momentum vector will be equal to the r vector. So r vector crossed by mv vector. So the mass is a scalar quantity, but the velocity is a vector quantity. And if we want to do this, you will have r vector, because we are taking the momentum about point O, which is this point. So we will be having a vector r from point O to the particle, and this is the direction of the vector, and you extend this vector from this point like this, and then you have the mv vector like that, and then you curl your fingers from r to mv, from the first quantity to the second quantity. So when you curl your finger from r to mv, you will find that your thumb is going up, which is positive. So you will have something like that. So you will have HO is going up because you have the direction is something like this, because you are curling your finger from R to MV and it will goes up. And this is how we get the cross product of the angular momentum. So what you can do, now we know the direction, it's in the positive k hat, so you can multiply R, the magnitude of R by the magnitude of MV, and then you put the k hat as the direction. And if you are given R as an XYZ, like has a quantity in X and a quantity in Y and quantity in Z, you can get the, here is I hat, J hat, K hat. So if you are going this way, multiply I by J, it will give you K. If you multiply J by K, it will give you I, and K by I will give you J, because try to curl your finger where with each one, it will keep giving you the other direction. But if you are going, so this is positive, and if you are going the opposite direction like this, so this will be negative. If you're multiplying I by K, it will give you negative J, and so far, so on. Okay, so this is for the angular momentum direction. So let's see the relationship between angular momentum and the moment of a force. So yesterday I showed how we can get the moment of a force, and I know that you guys know this basics from statics or physics. So if you have, like, this is a bar and there's a force is pushing this way, so the moment will be in this direction. So can you see? This is how it bends, so the moment will be in this direction. If a force is pushing this way, so the moment will be in this direction. So this is the curl direction, but we want to know what is the direction as a K hat or J hat or I hat. So if the moment is in this direction, can you see my finger? My finger is going this way, so it's a negative. But the force is, if it's going this way, sorry, I should use my right hand. So not, you don't use your left hand, because the regulation for the positive and negative is based on the right hand rule. So here is like my force is going this way, so my finger is towards me, so this is the direction of the moment. But if the force is going this way, so it will be the thumb is going the other way. And to know this, we will have to get the, like, from this, if you want to get the sum of moment, like for example, this curve, you have this force, and this is the R vector from point O to the particle. So the sum of the moments about point O will be the R vector cross product by the force vector. So if you have this, you have the F vector is going up and the R vector is going this way. So what will you do? You will extend the R vector like this and curl your right hand from R to F, and you will find that the sum of the moment will, your thumb will be going this way. So if you, from R to F, you will find it's, the curl is in this direction, and this will be the direction of the sum of M1. So this is how we can get the moment about point O. And this makes sense because the force is going up, so the moment about O will be like this, so my finger will be in this direction. So let's find how can we relate the moment O and the HO for a particle. So let's first analyze the sum of the moments about point O. So as we just explained, that the moment, so let's write a header here, the relationship between the moment of a force and angular momentum. So the moment of a force equal to R cross product by F, or we can make it the sum if we have multiple forces. So the sum of all the forces. And we know that F is equal to MA, and this is F vector, and we know that A is equal to V dot, the time rate of change of the velocity. So this will be equal to R cross product by the sum of the masses multiplied by the time rate of change of the velocity. So let's get the, we know that right now, we know that HO equal to the R vector crossed by the MV vector. So let's get the time rate of change of the angular momentum. Just like I need you to be able to differentiate between the moment of a force and the angular momentum on a body. So the angular momentum is a body is related to the linear momentum, and the moment of a force is related to the force on a body. So if we get the time rate of change of the angular momentum, so it's two quantities. You will get the derivative of the first one multiplied by cross product by the second quantity plus the first quantity, the first vector cross product by the time rate of change. So we can get the mass outside, and it will be dv vector dt. So this will be equivalent to r vector dot, because we differentiate with respect to time, and this will be cross product by the mass, and we know that the velocity vector is also r dot because it's the time rate of change of the position, and this will be equal plus r vector cross product by m, and this will be v dot. And from the definition of the cross product, if you have two vectors, like you have r vector dot, cross product by the same vector, because they are in the same direction, and the, like, if we said, like, if we have a quantity c vector is equal to a vector cross product by v vector, this is equal to the magnitude of vector a multiplied by the magnitude of vector b multiplied by the angle theta between them. So this is the magnitude of all of these. So the sine theta between these theta is equal to 0, and the sine theta will be equal to 0, so the quantity will be equal to 0. It's just like assume that you are multiplying I hat by I hat. So I hat by I hat will be equal to 0. So if we need a quantity, so I should be multiplied by a perpendicular vector, like I multiplied by j or I multiplied by k. So all these will be equal to 0, and this will leave us with that HO dot, which is equal to the time rate of change of the angular momentum, is equal to R cross product by MV dot. And this will be equivalent to this quantity, R multiplied by the sum of MV dot. So the time rate of change of the angular momentum will be equal to the sum of all the moment about point O. So this is the conclusion that we have. The time rate of change of the angular momentum will be equal to the sum of MO, or we can write it that the sum of the moment MO is equivalent to the time rate of change of the angular moment. And this is similar to the Newton's second law. Like you have Newton's second law is something like the sum of the forces is equal to the time rate of change of the linear momentum. So this is the linear momentum, and this is the angular momentum. So here's moment, and here's forces, here's angular momentum, here's linear momentum. And from this, we can do something like what we did before into the angular momentum. We can have dt here, and we can have dt here. So you will end up with that the sum of the moments about point O multiplied by dt will be equal to dho vector. And if you integrate these two quantities from time t1 to t2, and this will be from ho1 to ho2, this will give you the integration from t1 to t2, the sum of the moment O dt will be equal to ho as a vector at 2 minus ho vector at 1. And we can have h1 in the other side, so this will give us ho1 as a vector plus the integration from t1 to t2, sum of the moment at O dt is equal to ho2. So this is the angular momentum and angular impulse equation, and we have a similar equation with linear momentum and linear impulse. And if we want to expand this expression or this equation, we need to move this a little bit down. Okay, let's keep it. So HO is equal to, and this is HO1 and this is HO2. So the angular momentum at position 1 or at time 1, it will be equal to the R vector 1 cross product by MV1, and this will be plus the integration from T1 to T2, sum of the moments about point O dt, and this will be equivalent to R2 vector cross product by MV2 vector. So this is the main equation that we need to use for the impulse, angular impulse and angular momentum. So the term is that has impulse is this term. So this is the angular impulse. So it's a similar like the force. Before we have the sum of forces, the T, and it was linear impulse. But right now we have moment, so it's angular impulse. And this term is the angular momentum at 1, and this term is the angular momentum at 2. So before we have linear momentum plus linear impulse will be equal to the linear momentum at position 2. Right now it's a little bit different with moment and angular momentum. So this is the main equation that we need to use. I just want to bring your attention that how can you take this moment? So like, for example, sometimes you get confused in having this moment. Let's have this example. So this is one of the examples that very good to explain how we can get the moment. So for this example, you have like a column like this, and you have cable like this. In this cable, there's somebody sitting here, and this cable is spinning around this column, and you have many of them like. So this amusement park ride, you will have your body have a weight like this, and you will have a tension in the road like that. And if let's assume if you have also a normal force, maybe a normal force like this. So if we want to take the moment about point O here, does any of these forces make any moment about point O? Can anybody answer this question?
Could you repeat it?
Okay, so does any of these forces, if we need to take the moment of these forces about these points, does any of these forces make a moment about point O? Like if I have here a point and here's a force, So if I want to get the moment about point O, I multiply this force by this distance d, and the moment will be F multiplied by d. I want to get the moment of these forces about point O. Does any of them do any moments about point O?
Wouldn't it just be the weight?
Okay, let's think about it. So if we are thinking about N and T, so N and T pass with O. So there's no distance between O and N and T. So T and N doesn't exert any moment. So we can agree on that T and N will not have any moment about point O. But let's think about weight. The weight is doing a moment about this whole thing. But if what we are thinking about, if this is the column that has the wire, we are thinking about the moment about this column like this. So this is the column, and we are thinking about the moment like this, not the moment like that. So the moment like this, weight is parallel to this one. So it will never exert a moment in this direction. So about the column like this, it will never do this moment. So this is something similar, like if you have a if you have a cantilever like that and fix it at this position, and let's make it 3D. And if you have a force going this way, so the force going this way will make a moment like this. And the force this way will make a moment in this direction. So just be clear about the direction of the moment. So when we talk about moments, so we are talking about the moments in this direction. So the weight will not be exerting any moment in the plane of motion, but it will exerting a moment here. So if this is if this column is fixed at this location, so it will make a moment like this at this location. And if you imagine that this is a cross section, like this, and this is the XY of the cross section, so the weight will be exerting a moment about this axis. But what we are thinking about the moment that's making something like this, not the moment that making something like that. So that's just like the mentality, how to think about how the moment is exerted on the particle. So let's see this in an example. So let's solve this quick example. Okay, so for this example, it says that we have 80-pound crate. So we have a crate of a weight, not a mass, of 80 pounds, is moving around a frictionless assembly. So we have a frictionless assembly here at point O, and it's in moving about this assembly, and make sure saying here top view. So when we say top view, so you have this assembly on the table and all of this on the table. So it is not vertical like this, it's something like that. So we are working on this plane, not this plane. Okay, so when we have like a plane motion, so we will not have a potential energy, like the bodies is not up there or down there. So all the system is in the plane. Okay, the crate is moving with at V1 of 0.5 meter per second. So this is the direction of V1. And in a straight path, so it will be like this, just after an arm begins to pulling. So this is like an hydraulic arm, something like this. And this hydraulic arm is keep going in. So just after an arm begins to pulling the crate from R1 2 feet to R equal 1 feet. So this arm is getting shorted by 1 feet from position 1 to position 2. So right now we have two types of velocities, one in the theta direction, which is V1, and one in the R direction, which is the V is going this way. So the best coordinate system to use with this problem is the R theta coordinate system. And here's keep saying that the crate goes from R1 is equal to 2, from 2 feet to 1 feet with a constant radial velocity of 0.4 feet per second. Does anybody know if we are saying that VR is equal to 0.4, is it positive or negative? Like here, it going this way. Is that a positive direction of the VR or a negative direction of VR?
I would say positive.
So why did you say that?
Because the motion is upwards.
Okay, so let's just think about it, and I will remind you with our r theta direction, positive and negative coordinate. So let's do this first. So when we talked about r theta, positive and negative coordinate system, we wrote something like this, and we have our body like this, and we agreed that the positive r direction should going from point O toward this the particle, and this is the positive r, and this will be negative r, and the theta should be in the direction of increasing theta and perpendicular to r, so it will be something like that. So this is the positive coordinate system. Let's apply this principle on this problem. So let's have our body like this. And actually, this is a mechanism. Shouldn't be fixed. So it's something like that. And we have our crate. And it should be a little bit short. Something like this. So here, if this is point O, and this is the direction of increasing theta. So if we have V1 equal 0.5 meter, actually it's feet per second. So let's see what is the positive and negative direction. So the positive direction of R should be going from point O to the body here and should be going this way. So this is should be the positive R direction. So it should be something like that. And sorry, this should be R. And theta should be perpendicular to R and in the direction of increasing theta. And we know that theta is increasing this way. So this is the positive theta direction. So if the arm is moving this way, so it's positive R. But if the arm is moving this way, so it will be negative R. So let's put the what's given. So what given is that at position 1, VR1 is equal to negative 0.4 feet per second. Because it's given that here it's 0.4 and the arm is shortened from 2 feet to 1 feet. So this will be negative 0.4. For theta, it will be V theta at 1 equal to 0.5 and it's positive feet per second. So right now you can write the V vector as negative 0.4 in the R hat plus 0.5 in the theta hat. And you can get the absolute of V by 0.4 square plus 0.5 square, and this should give you 0.64 meter per second. Okay, so this is at position 1, and what we need to do is that we need to get at position 2. So at position 2, the VR, it's saying that with a constant radial velocity. So the radial velocity is constant, hasn't been changed from position 1 to position 2. So we know that the VR2 is still equal to negative 0.4 feet per second. but we don't know v theta 2. That's what we need to find out. So what we will use in this problem? The best strategy to solve this problem is to use the angular momentum principle. Why? Let's look in our equation. Our equation says that HO vector 1 plus the integration from time t1 to t2, sum of the moment of all the forces that we have dt is equal to HO2. And if we expand this equation, it will be R1 vector crossed by the MV1 vector plus the integration from t1 to t2 Okay, so let's see if we have moments or not. So let's just make sure this is a top view, and let's assume that we have our crate like this, and there's a tension in the bar, and this bar like this. Let's assume it's force F, and you have a weight is going down, weight, and let's, if this system is resting on a table or something, so this weight will be going like this, and the normal force will be going up like that. And what we need to do is that we need to find the moment about point O in the direction of motion. So we have all our system is moving in this plane, and this is the direction of the motion. So we need to get the moment in the direction of the motion, not the moment outside the direction of the motion. So the weight and the normal force is not exerting any moment in the direction of the motion. And the force F is passing through O. So F will be, the moment will be done by F will be equal to 0 as well. So all the moments in this problem will be equal to 0 because the weight and normal force is exerting moment outside the plane of the motion, and the force F pass with point O, and this will be giving us moment equal to 0. So we will be left with the angular momentum terms. So let's solve the angular momentum terms. So for the angular momentum terms, the R1 of the arm was equal to 2 feet. So we will be having 2 feet, and the direction of the 2 feet is in the R hat direction because it's the R hat direction. And it's a positive quantity. And then this will be cross product by the mass M multiplied by the V1. So the V1, we have it here, negative 0.4 in the R hat direction plus 0.4 plus 0.5 in the theta hat direction. So we got V1, and just make sure that the mass is multiplied by this vector as a dot product, not a cross product, because the mass is a scalar quantity. And this will be equal to R2. R2 at position, so this is position 1 and this is position 2, the R was equal to 1 feet. So it will be 1 in the R hat direction, and this will be multiplied cross product M, and you will be having V2, and for V2, you know the VR2, it's a negative 0.4 in the direction of the R hat, but we don't know the V theta 2, which will be in the theta hat direction. So let's see how can we solve this. So the mass will be done with the other mass on the other side if we divided the whole equation by M, and this will leave us with the cross product of 2R hat by this vector. So multiplying R hat by R hat, or theta hat by theta hat, or I or J by J or K by K, all of these will be giving you 0 because they are in the same direction. So R hat by R hat will give you 0. But R hat by theta hat, so let's assume that we have the r hat in this direction, and the theta hat in this direction. If you multiply them cross product, you will curl your finger from r to theta and should be give you another vector perpendicular. So it will be something like this, and the vector will be in this direction. So towards you, and we call this k hat. Okay, yeah, it's something like you have in the plane, you have r hat in this direction and theta hat in this direction, and the vertical direction is k hat. So when you multiply r by theta, it will give you k hat. So when you multiply these two, it will give you k hat direction. So the multiplication of r hat by theta hat, 2 by 5, it will give you 1, and this one will be in the k hat direction because this is the resultant of r multiplied by theta. And this will be equal on the other side. You have r hat, and here's r hat, so it will be 0. And r hat by theta hat, it will be give you k, so it will be 1 multiplied by v theta 2 in the k hat direction. So this means that v theta 2 is equal to 1 feet per second. So right now we can know that the velocity v2 as a vector is equal to vr2, which is negative 0.4 in the r hat direction, plus 1 in the theta hat direction. So this is v2, and if we want to get the scalar quantity, so it will be 0.4 square plus 1 square, and this should give you 1.077 meter per second. So this, I think it's the first requirement in the problem. What is the velocity vector in r and theta component of the motor at A? So you have a motor that gives a work on this body to move it from position 1 to position 2, and it changed the total velocity at V1 and V2. The second requirement is how much work does the arm do? We need to know how much work does the arm do to move this crate from position 1 to position 2. So we will have to move to the work and energy. So based on the work and energy and the principle that we have about work, the kinetic energy at position 1 plus the sum of the all work exerted from 1 to 2 will be equal to the kinetic energy at position 2. And we have V1 and we have V2. But let's see what forces that we have that might exert work. Okay, so is there here any spring? No, there's not any spring, so there's no spring force. Does the mass of the body exert work? I mean, like mgh, or the weight exert work? So all this problem is in the plane, like on the table. So there is no any masses that goes up or goes down. So there is no any change in the potential energy, or there is no any delta y to multiply the weight by. So there's not any work come from springs or any work come from the weights, because here's a special case. It's a plane problem, not a vertical problem. So it's only the work exerted by the motor. So we will keep it as it is, and we will have.
Did it say in the problem that it was a plane problem, or was it?
Yeah, it says here it's a top view. So just keep attention. Many problems.
Oh, okay.
Top view, side view. So if it's saying this is a side view, that means that this problem is standing like this. And sometimes you have the weight starting from here and go up there. So there's a change in the potential energy. But once it's a top view, so all the masses is moving on the table. So there's no change in the energy. Did you got it?
Yeah.
Okay. So here, let's move to the work and energy. So we'll be having half mv1 square, and this will be plus all the work exerted by the motor will be equal half mv2 square. So if we need the work from 1 to 2, it will be half multiplied by V2 square minus V1 square. And this should be equal half. And we have the weight is 80 pounds, so we need the mass, so we'll divide by 32.2. And we multiply by V2 squared, which is 1.77, minus V1 squared, which was 0.64 meter per second, square, and this should be equal to 0.93 pound-foot with a unit of work. So this is how to solve the work as a bar. So what we did, we get the V using the angular momentum, and then we use the V for the kinetic energy to get the work. Then the requirements say how long does the crate take to get from 1 to 2. So we need time. How much time does it take the crate from 1 to 2? You can get the change in the velocity, and you will have to know how much distance. So it will be very complicated problem if you look in the distance on this side, because it is not a circle. It is not a circle like this. It starts with R and end up with different R. So it will be a very difficult problem. But what's given here actually, you are given VR, it's 0.4 as a magnitude feet per second. And you know how much distance that the arm get from position 1 to position 2. So the delta R is equal to R1 minus R2 or R2 minus R1, but we are interested into the change. So it will be 1 minus 2, it will be -1. And you have this as a negative velocity. So the time will be equal to the VR over delta R. So you know how much that this arm, how much length it change in the arm. So it was 2 feet and become 1 feet, and we know the velocity. So we divide the velocity by the change of the R, and this will be equal to -0.4 over, oh, sorry, it should be, so let's start by VR. VR is equal to delta R over time t. So if you need time t, it will be equal to delta R over VR. So I just made a mistake and put the VR up there. So if you confuse it, start by diversity principles like this, and you switch t with VR. So delta R will be equal to -1 over -0.4, and this should give you 2.5 seconds. So this is how much time it takes the body to go from 1 to 2, and this is the easiest way, because we don't know the theta, how much change in the theta, so we cannot go in this way, but we know how much change in the R direction. All right, so does anybody have any question about this problem? All right, so let's move to another topic. So what I was planning to do in the next 15 minutes is just like to start chapter 16, but I will not start chapter 16, but I will revise some concepts that we will need for chapter 16. But we can write chapter 16 here because and chapter 16 is the planar rigid body motion. Okay. So before we start this chapter, I would just like want to revise some concepts with you about the angular velocity and the angular expressions. So right now, till now, we dealt with many things. So let's put a table here. And this table will have the most important three quantities that we dealt with, which are the displacement, velocity, and acceleration. And we did this with linear and angular format, or we sometimes say this is angular or rotational. Okay, for linear, we have the displacement described by S. So let's assume that when we say linear, so we have a body. So this is the linear, this is the rotational, and this is linear. So for the linear, we have our body here, and this body moves this way until it gets here. So start from point O and move until it gets to distance S. So this we call it S. But if we have a body here and move to this point here, so we describe this body by the angle radian. Sometimes you can describe it that say that this body moving this curve with a distance S. However, if this body moves this S and did a 2 by, he will get, so if he came here and then here and then here and then came back to the same original point, so the S will be equal to 0. So the measurement that we have been using in linear motion will not work for rotational motion, because you will end up with that S is equal to 0. However, this body may did 5 or 6 cycles around the circle. So we describe this by theta, that this body is made a 1 radian or 2 radians or 2 pi. 2 pi is also a radian. So we measure the angular distance by theta, and that theta shouldn't be an angle, it should be radians. Okay, and talking about radians, so let's just like revise this concept about the radians. So all of us know that if we have a circle like this, and this is the center of the circle, and you start your motion from here, and you get here, if you were able to cut distance, this distance, r equal to the radius, so if the length of this curve is equal to r, so the angle here will be equal to 1 radian. If you were able to do 2r on this curve, another 1, so it will be 2 radian. If you were able to do an angle of 2 pi from here to here, so this angle is equal to 2 pi radian, so you will be cutting a distance of 2 pi r, and 2 pi r, which is the circumference of the circle. So this is how the concept is working. Like you moved 1 radian, so you did r, 2 radians, you did 2r, 3 radians. If you did 2 pi radians, you will be doing 2 pi r. It's something like 1 radian gives you an r on the curve, and if you did 2 pi, you will be given 2 pi r. So this is how this concept work. Let's get to the velocity. So the velocity, if this body was able to get to this point 1 in time t, so the velocity here will be equal to s over t, and this will be equal to the velocity. But if we are working with a rotational motion, So we describe this with this theta over time t. So here, how much radian angles that you did in time t, and we call this omega, which is the angular acceleration, but v is the linear acceleration, and this is in radian per second, and this is in meter per second. This is meter, and this is radian. So this is how we measure omega, like how much angles that you did over the time. So with this, you will be able to know how much time does it take to do a one cycle around the circle. And if we want to know this, how much time you take to do one cycle, so the omega will be equal to, not the omega, like if we want to get the velocity v of this body, and if this body made a distance, like if we are not talking about radians right now, if we are talking about distance, and this body was able to do one cycle around this circle until it get here, so he made a distance 2 by r, and we divide this by time t, and we call this t is the periodic time because it's only one cycle. And the periodic time by definition is the time that the body takes to do one cycle. So, and moving from here to here, it gives you this. And we call this part 2 pi over t, because 2 pi is the angle that this particle move. And if we divide 2 pi over t, it will give you omega, because this is the how much radians that the body take to make one cycle. So v will be equal to omega multiplied by r. So, and this is what we learned from before. So this is how we can move from a linear velocity to angular velocity. So the linear velocity will be equal to the omega multiplied by r. So let's draw this circle again. Also, it's not a circle. And let's assume that we have, this is the center, and we know the omega, which is the 2 pi over t. So the velocity will be something like this. Like, let's have it in this direction. And this velocity will be equal to the omega, because this is 2 pi over t, multiplied by r. So it will give you r here, which is the circumference of the circle, omega by r. And it keeps changing in direction. It was here and here. At each one, the v will be something like this, perpendicular to the r direction. And this rule, v equal omega by r, only give you a magnitude, doesn't give you a direction. If you want to get a direction, so you will have v vector will be equal to the omega as a vector cross product by the r as a vector. So let's think about this in a vector shape. So you have your circle like this, and here is the center of the circle, and you know the omega direction. It's this way. So if you want to know the direction of the omega, you curl your finger with the omega, so it's positive, so the direction is going outside. And this is the r vector is going this way. So this is the r vector. If you want to get the velocity direction, so you have r is going this way, and you have omega is coming out like this. So you will have your system like that. So you curl your finger from omega to r, so you will have the velocity going this way. So you will have your velocity is going this way. And if you are like, for imagine that you are here. So omega multiplied by r, you have omega is coming outside like this, and r is coming like this. So you multiply omega, so this is omega and this is r. So you curl your finger from omega to r, so your velocity vector will be going this way. So this is the velocity vector. And this makes sense. Why? Because you have your body is moving like this. So the velocity is going this way, moving with the circle. So you have omega is going this way, so the velocity is always in this direction and keep changing in this direction. So you either do the cross product or you see how does it make sense in terms of the velocity. So it nevers that you have omega is going this way and the velocity is going down this way in opposite direction of the omega. And if you are confused, set the r vector and set the omega vector, and then multiply them cross product and see what is your right hand rule telling you to get the direction of the v. So this is some just like revision on how you can get directions. And for the acceleration is equal to v over time t, and it's meter per second square, and we call it a. And for the angular acceleration, it's omega over t, and this is equal to alpha. And this is radian per second square. All right, so let's note based on this that v is equal to 2 pi r divided over time t, and we know that 2 pi over t is equal to omega multiplied by r. And I want to bring your attention to the quantity 1 over t. Like we know that omega is 2 pi over t, and this is equivalent knowing that the frequency is 1 over t. So what is the frequency? The frequency is how much cycles that the body do in 1 second. So if the frequency is like, let's assume that the body takes half a second, so t is equal to 0.5 seconds to make 1 cycle. So the body move from this point and go all through this circle in half a second. So how many cycles will be done in 1 second? So half a second you will do 1 cycle, and another half a second you will do another cycle. So if you divided 1 over 0.5, it will give you 2. So this is the frequency, how many cycles you will do in 1 second, and the units is per second, or we call it second negative 1. So it's 2 cycles per second. So this is the frequency. So the omega is equal to 2 pi, and 1 over t will be equal to the frequency. So sometimes you will be given the frequency in the problem, so you will know, if you multiply 2 pi by the frequency, it will give you omega. And if you multiply the omega by r, will give you the velocity. So this is how it works in the problems. You sometimes given the frequency, sometimes you will given the angular velocity. You should know how to switch between these things. And you remember actually this from the tangent normal acceleration. If you recall, when we have a normal is equal to v squared over r, or we substituted this with omega r, and it was equal to omega square r square over r, and we finally end up with omega square r. So we have omega square r, or omega square r square over r square, or v square over r. So all of them should work for the AN. So this is just like a quick refresh on your memory, how you can move from linear acceleration to angular acceleration, and how you can use your right hand rule to get the direction of the omega or the direction of the velocity, and how can you switch between the different types of motion, either it's linear or it's angular. Does anybody have any questions so far on these concepts? All right, so we will have a help session at 1 p.m. today. If you have any questions in the homework, if you are studying for the midterm exam, just come with your questions and I will be there answering your questions. And tomorrow we will be continuing chapter 16. And I think we will have 30 minutes. So I will be using the first 30 minutes to do some introduction to the rigid body motion. and the next 30 minutes will be for your quiz, and the quiz should cover chapter 13 and chapter 14. We will have a problem on a chapter 13 and another problem on a chapter 14. And I think one of the questions you will have, I don't know if both of them, but at least one of them you will have to upload your answer, and there will be 11 points as a partial credit. All right, guys, good luck with your quest tomorrow. See you guys in 2 hours if you would like.
Thank you.
Thanks.